Welcome to Science Bytes, a podcast from Australia's leading supercomputing and big data research facility, the National Computational Infrastructure. You'll be hearing from some of our users about their careers, their scientific research, what excites them about the work they do, and how supercomputing and data technologies help them make scientific discoveries. Coming from all around the world and from a huge range of scientific disciplines, they are the people behind the science headlines you see every day. And now, here's Andy in conversation with today's guest, Dr. Brad Tucker.
Thanks for joining us today. Dr. Brad Tucker is a fellow at the Research School of Astronomy and Astrophysics at Mount Stromlo Observatory at the Australian National University. He's also developed astronomy coins with the Royal Australian Mint and consultant on sci-fi movies. What a way to make a buck. How are you today, Brad?
Good. How are you?
Not too bad. Where do we find you today?
So I am currently in between working from home and my office, in between random meetings and stuff like that. But I am based at Mount Stromlo. The background behind me, obviously, it's daytime when we're recording, and so it's nice to have the beautiful nighttime landscape here with the star trails kind of above my head. So this is the mountaintop where I work essentially daily.
As far as Zoom backgrounds go, I couldn't imagine anything better for you. That's
Exactly.
Brilliant. Now, I actually have been to Mount Stromlo many, many years ago, around 2001, I think, or 02. But of course, back in 03, there was that dreadful fire that ripped through Canberra. How's Mount Stromlo looking now? And how's the observatory and everything looking? Because you lost so much in the fire.
Yeah, look, Mount Stromlo has the unfortunate record for being the largest single insurance claim in Australian history due to the bushfires. It's one of those records you don't want, but you have. We say we are rebuilt. It doesn't mean we're not doing more projects, but everything that was going to be rebuilt in the way has. But that doesn't mean we're still not looking for new options, new ideas, new projects to do, but most of the buildings and stuff like that are rebuilt as much as they're going to be.
Oh, brilliant. So let's get into a bit of your backstory. So what first interested you in astronomy, Brad?
Yeah, so I kind of came to it late. It wasn't something where growing up as a kid, I wanted to do astronomy or anything like that. I fell into it at university in that I went to university, I studied physics. I also did philosophy and theology. And, I was doing different areas of physics. I started off in an area called spintronics, so what we call solid state or condensed matter physics. It was a really cool idea, just wasn't my style. That was when I found it. I was like, hey, I'll try astrophysics. That sounds fun. And then it worked. I liked it. There are some people who work here who are like destined to be here from the beginning. Know they wanted to do as a child or growing up. I just fell into it at university.
Yeah. Oh, brilliant. So where did you study?
Yeah, so I did my undergraduate in the U.S. at the University of Notre Dame. We don't say it properly. We don't say Notre Dame. So I did physics, philosophy, and theology. So I did 3 there. And then I moved to Mount Stromlo, where I am now, to do my PhD. And then after that, I went back to the U.S. and then came back. So I've been at Mount Stromlo for quite a while now. Originally coming just to do my PhD and now on staff here.
Brilliant. Why would you say that astrophysics is important for the average Australian?
There's always a major line that people always quote, which is fair, but I think there's also another important tone that we need to have. We often talk about the technology that's developed out of astronomy and astrophysics, the mathematical tools, the computational tools, the engineering, the telescopes, the equipment. A lot of this stuff finds its way into so many different areas that transforms our lives, and it's always an amazing thing. But we also then, I think astronomy and astrophysics is a great summary of that desire to understand and know the role of the universe and be inquisitive. And that is the means, right? As in, we don't necessarily have to justify, I feel, that nature. That's what makes us human.
Yeah.
And, humans have, for eons, looked up at the stars and wondered and studied and looked and measured and believed and dreamed of. And it's such an ethereal part of the human experience. And, what we get to do is to understand these complex things, see away these far or amazing things. But then at the same time, there's phenomenon that you can see with your own eyes. And there's so few areas in astronomy and in space or in science that you can see something and then see it as part of a very complex phenomenon with your own eyes. From the way the planets move to the seasons, there's so many subtle things that happen that are because of complex physics.
Yeah.
Yet you get to experience it with your own eyes. And a lot of other areas don't have that opportunity.
It's true. I remember the first time I ever saw through a telescope the rings of Saturn. It was a real life changer. It was like, wow, there's photons that have shone from the sun all the way over to Saturn, back to me, into my eyeballs and my eyeballs alone. It was a huge and simultaneously very intimate moment.
It is. And it looks exactly as advertised. Like, that's
Yes.
the amazing thing, right? You see pictures of Saturn, and it's like, that's what it looks like. And you're right. It's not that, it's been enhanced or we had to zoom in. If you look at it with a telescope, that is exactly as we see it. Again, it's that connection, I think, that is an important, powerful experience that, again, is so rare that we often have in science.
Yeah. And of course, you wouldn't just be using a borrowed National Geographic telescope like I was. You have access to the full monster truck capabilities of the systems at NCI. Must be amazing. Which systems do you use there, by the way?
So we use Gaddy. We also used to use Rajan as well.
Yeah.
A lot of our software is still on Rajan. And this is all because, so what I do, there are a lot of people in astrophysics who do just computational stuff, modeling, simulating, to know what the questions and predictions should be. And all of that is done on these supercomputers. I'm an observationalist, so we measure and observe things, look through a telescope. But I think, people have this view that we sit with our eye through a telescope. That is not at all what we do. We have projects like SkyMapper that uses the NCI facilities that are constantly mapping the southern skies digitally. So they're kind of taking images constantly every night, repeatedly over and over and over again. And there are so many objects, we're talking about quite literally hundreds of millions of objects that are being measured, all the time. You cannot do that by yourself. You cannot do that by eye. You cannot do that on your computer.
Yeah.
You need sophisticated algorithms and the computing power to process it, to analyze it, to collect it, to measure it. So it's kind of the nice thing that, you set the telescope going overnight, and in the morning you have all this nice new shiny data to look at, all because you have a supercomputer that can process, manage, handle, store, display, treat, all these sorts of things. You just couldn't do this by an individual human.
And what other projects are you working on at the moment that involve big data?
One of the things we've been using with the SkyMapper facility is trying to find, this was an early project, Planet 9. So this was a potentially theoretical 9th planet in our solar system.
It's supposed to have some crazy huge orbit, right?
Exactly. So we think that it could take 30,000 years to orbit the Earth, and it's very far away. It's not even like finding a needle in a haystack. It's like finding a needle in a haystack that's buried in the ocean, and you don't know what part of the ocean, right? It's just, it may not even be there, right? And there not even may be a needle. It may be a thumbtack, right?
Wow, yeah.
It's so many different things. So you have to do all of this monitoring and processing. We've also then been using telescopes at Siding Spring to measure what's called dark energy. This is a property of the universe that is causing the universe to accelerate. So 70% of everything in the universe is this thing we call dark energy. And it's kind of like gravity in reverse. So instead of sucking things in, it pushes things out. And so in order to map the properties and strength of it, you have to map all across the universe, supernova, exploding stars.
Ooh.
And again, you don't know when and where a star is going to explode. So you're constantly imaging the sky, taking new images and looking for subtle changes. It's an elaborate game of spot the difference, just with supercomputers.
Yeah, that's amazing. So when it comes to the day-to-day experience of a computer like that, like my experience of what I thought a high-performance computer was like the kick-ass MacBook Pro that I bought at JB Hi-Fi. But what's your experience of a high-performance computer? What do you look at? What's the day-to-day workflow like?
Yeah, so a lot of it is checking the measurements coming out. I mean, there's so much data that we can't even look at every image a telescope takes by eye anymore. It's just not feasible.
No.
And in fact, projects are ramping up that even most of the data won't even be able to be saved. It'll just have to be processed in real time by these supercomputers. So, we kind of get a list of measurements where we say, hey, if we're looking for new supernova, all right, we'll get these little cutouts that say, here was the before image, here was the image we think with the supernova, here's the difference. And then you have to vet a little bit, is it real? And then you get the automatic measurements of the brightness. So supernova change with brightness over time.
Yeah.
So you're looking at plots of data as the supernova changes over time. And then sometimes it's kind of then making sure that it's uploaded into a database. So it's a lot of database management, again, of these measurements, because you're not looking at these individual objects by eye really, other than in the rarest cases. So it's a huge volume of measurements and numbers coming in that you have to deal with, and setting the code running. So when you submit these jobs individually or as automatic jobs to the system, it's kind of a bittersweet moment. You spend writing the code, getting everything prepared, you send it off to the supercomputer, and then that's it. It's not like you get this image all of a sudden on the screen, you send it off, and then all of a sudden, a little bit later, all of the data is just right there. And now that's actually that's when the science starts. And
that's the Christmas morning for you.
Yeah. That's the thing with, these supercomputers. It's making the science expedited, right? Instead of spending all this time to get to the point to do the science, it makes all this stuff in between happen so you can focus more on the discoveries and knowledge.
And I suppose the speed and the power of it would also broaden the capabilities of what you're able to contemplate and what you're able to ask, what questions you're able to ask.
Exactly. That's right. Just to put in the scale with computing power and telescopes, searching for supernova 10 years ago, 12 years ago, required us to be able to find maybe a couple of hundred supernova over 5 years. We're now finding hundreds of supernova a night.
Oh, wow.
Exploding stars, all across the universe. So you could just dramatically measure deeper into the universe, wider patches of the universe, more chunks of the universe. And so, what my area is, which is trying to measure the properties of the whole of the universe, this is really critical because you want more area, more depth, more volume, more data, more measurements. And so by having, these increases in computing power, it allows you to ask those bigger questions and get those more accurate answers. Going from, hey, it's maybe to within 10, 15%, we may know an answer. Now we're looking at answers 1% or less, so our accuracy in the measurements is improving as well as what the questions we can ask.
Yeah. And what are some questions that you're looking forward to asking that you haven't gotten to yet?
So I think there's a few new areas where we're really trying to pinpoint what's going on. One of the big differences in this area that we're looking at is if we measure how fast the universe is growing very early on in the history of the universe, and we look at it today, those answers are different. And we can't reconcile why those answers are different. There's a huge, what we call controversy in the field, because it either means the stuff that we know of in the universe is doing something differently than what we thought. It could be that there's something entirely new in the universe that we've never discovered, a new substance or material. Or it could be that our calculations and our measurements are wrong. And all of those are very possible. The only way to do this is by more measurements of different types, both nearby and really far away. And so in order to make sure the measurements aren't wrong or we haven't made a simple mistake, we have to go now to tens of thousands to hundreds of thousands of measurements per night to do this. And so new facilities that are coming online to help with this, like the Vera Rubin Observatory in Chile, they will be finding objects in the sky, supernova, exploding stars, things that go bump, thousands to tens of thousands or hundreds of thousands a night. And what happens is they're discovered in Chile. We then have to be alerted in Australia. And Australia is a perfect place because Chile will take the image, realize it's real in real time using their supercomputers, then tell us, hey, we think this is real. Can you go confirm what it is, what it's happening, what it's going on? And we have, literally 6 hours in order to take the image, reduce it in Chile, figure out what's going on, tell us, then tell our telescopes in Australia to go look at this, analyze it, and tell us what's going on. by the time nighttime rolls around again in Chile. So all of this has to happen in less than 24 hours.
Yeah.
And so, now we're relying on these facilities to automate, manage the telescopes, do it, deal with it, talk to the other databases so we can expedite that process. It's a mass manufacturing almost style of doing science now.
That's amazing. And it's only going to get more amazing. So as the supercomputers continue to get more super and high-performance computers continue to get more high performance, what advances are you looking forward to being able to be a part of and to see in the coming years and decades?
Yeah, again, it's really now starting to look even further back. Now these measurements, which we've done in the nearby universe, we can now go look at the universe when it was like 7 or 8 or 10 billion years old.
Mm-hmm.
And then it's now as new telescopes come online, where we can then have these high performance computers that can manage and talk to each other. We can now, as new space telescopes are coming online, really get that data in real time almost from those space telescopes sent to us, so we can do the measurements. Whereas before, sometimes it would take 4 to 5 days. And so you can only look at a handful of objects. And one of the very specialties that I like is finding stars within the first hours that they explode. So when a star explodes, there's this massive shock wave that rips apart the star, kind of like the flash of a nuclear bomb. And that flash, which lasts literally for hours at best, tells us all of the properties that we need to know of the star. And this is very critical for our measurements. But generally, we don't catch on till 4 days, 5 days, sometimes 2 weeks after.
Mm-hmm.
So now with the high performance computing, we can do all of this hopefully to within an hour, if not less.
Yeah.
Then we can actually see literally stars as they are exploding, like in the process of dying and being ripped apart, which just gives us clues of physics and parts of the universe that this idea has been around for decades and we just never thought we could access it, but we can now.
As an aside, have you been looking at black holes along the same methodology?
Yeah, and one of the things that we're also doing with black holes is measuring how often black holes change. Mm-hmm. So we often actually think of black holes as just sitting there and, hanging out, but they actually swallow and change and change their environment, sometimes on scale of what we're now realizing is minutes, not just weeks or months, but literally hours to minutes. So what we want to do is to measure it as often as we can to see how often a black hole is eating and destroying stars, how they're growing, how many they are, the volume that they can do. And again, as quickly and as often as possible. We want to see it as quick and as much as we can. And the only way you can do that is with high performance computers to manage and deal with that data. Previously, again, you can only do it every couple of days, but with these new facilities like Gotti that you have, you can take an image multiple times per night, and hopefully we can get that down to a couple of times per hour, which just opens up our view of the activity and strength and physics and science of these things. Again, we're kind of seeing the secret lives of black holes and things in space.
That's amazing. And getting back to your studies, you mentioned that you studied philosophy and theology as well as astrophysics. Are there any philosophical questions you've been able to find new insights into through your work in astrophysics?
Yeah, this is an interesting thing because, I think when we start talking about then the idea of the Big Bang and, how did the universe come to be, a lot of these questions are philosophical because we just don't have the mathematical or physical tools to try and to answer it. But as our facilities get bigger and more powerful, we're pushing back the boundary of how far and how deep and how much we can see. And, there are now maybe options that we can do that. Again, we just didn't really think we could make that measurement. But nowadays, maybe it's not as far off in seeing the beginnings of some of these activities in the universe. And so that's, again, the exciting thing. There's just stuff that we thought was probably inaccessible. Mm-hmm. And so it was always this great philosophical conundrum, which really goes then to the existence of the origin of the universe and how we measure it and how we understand it, to now there may be ways of testing it. And I think that, again, it just changes our view of everything. And I think that's an exciting thing about it.
Yeah, there's still a lot of mystery from, even my layman's understanding, things like what we used to call the Big Bang, starting from like a singularity, a tiny little dot, that doesn't seem to be the way things actually happen now. It's more like a big whoomp, I guess.
It is a big whoomp, and there's this period we call inflation where the universe grew, rapidly in the scale of a fraction of a second. And we're starting to push that boundary of the calculations of what's happening during that period, and then potentially the observations. And that's why, again, high performance computing is critical. Is if you're trying to simulate how the Big Bang or the universe evolved in the early days, there is no other way to do that besides a high performance computer.
Yeah.
You cannot run it on your iPhone or your home laptop, right? You need a lot of power. If you're quite literally trying to simulate parts of the universe, that is the only way. And here, the more power and data you have, the more detailed you can make the simulations, which then we can go and say, all right, can we do an experiment with our telescopes to prove or disprove that? And that's kind of this critical juncture we're at now. It's not just for dealing with the data, but making the predictions and calculations as well. And both need high performance computing. All of the students in my group, even the small high performance computers that we can access, or the older ones, everyone's always submitting jobs with it. It's no longer a job of just running something on your laptop. That is not the world this field lives in anymore.
That's amazing. And I'm totally going out and copywriting the big whoomp, by the way. So with your work, what do you love most about the work that you do?
I like some of the intersects that we get to have with the public, and again, some of this is all because we can manage, display, and deal with the data in a sensible way through these facilities, through initiatives like citizen science, right?
Mm-hmm.
Getting the public involved in searching for supernova, or a few years ago with Planet 9, we can do these things where we were trying to look for this planet. Between being able to process the data quickly through high performance computers and then people vetting and by eyeballing, checking, is this real? Is this not? They did 4 million classifications in 3 evenings. They did what it would take a PhD student or 2 PhD students to do in like 3 nights. And you can just do things. And so it's this beautiful combination now of having this most advanced technology and then being able to make the data and information accessible in a way to the public that, again, we just never previously could do en masse, that is dramatically changing those questions and ideas that we can and cannot do.
Fantastic. And are there any curly cosmological questions that keep you awake at night, Brad?
Look, I would say the biggest one is, why is our universe different speeds at different times? This really will potentially just transform knowledge. It will either open up a completely new thing that we just never thought, or it will tell us something, just kind of change the whole playbook on something we currently think. And so kind of either way, we're realizing there's a big answer here. We just don't know what that big answer is. And that's the exciting bit, I think, is we're not even points now where we know kind of, all right, yeah, we think that's the answer. We just have to prove it. There are some questions where we just generally have no clue, but we know there's a question to solve. And it's going to transform our view of the universe one way or another.
Looking forward to the coming years and decades and the discoveries to come.
Exactly. Same here.
Dr. Brad Tucker, thanks for your time.
Thank you.
And a big thanks to you, yes, you with the earbuds in, for listening to Science Bytes. You can keep up with Dr. Brad Tucker on YouTube and Facebook, and btucker22 on Twitter. You'll find out more about NCI on Twitter at NCI News and on LinkedIn as National Computational Infrastructure. Bye for now.